Okay, let's go.
In 1991, Metro DF was founded, becoming crucial to the public transportation system of the Federal District. Today, it operates 42 kilometers of tracks with 27 stations on two lines, Line 1 green and Line 2 orange. The trains, divided into two types, series 1000 and 2000, have distinct characteristics requiring different levels of attention. In total, the company owns 32 trains. In 2022, they carry around 39 million passengers, and the revenue reached nearly $38 million, a substantial increase from the previous year. As promoters of sustainability and innovation in the sector, they implemented solar generation in 2 stations, launched an app for system users, and modernized the ticketing technology. Its maintenance, the heart of the company, employs daily monitoring techniques and fault correction procedures. However, the aging infrastructure poses significant challenges, such as increased maintenance costs, making low-cost solutions a good option to balance the need of modernization and expenses. In this context, the prospect of a low-cost device capable of preliminarily identifying defects in the tracks and monitoring them appears promising.
We are at the Administrative and Operational Complex of Metro DF, located in the administrative region of Águas Claras, in Federal District.
Here is where the administrative buildings, the operational control center, and the workshops are located. And today we will show you how the rail monitoring of Metro DF works.
Failure detections on tracks at Metro DF uses several methods, such as acoustic emissions, thermography, ultrasound, and inspections by foot. Occasionally, a special vehicle is used to identify track and geometry problems on the rails. But most of monitoring systems are done visually by foot inspections. And to understand how it works, let's go there.
It is 2 a.m. and we are ready to demonstrate how is done the visual inspection in our lines. The visual inspection on foot occurs daily at Metro DF. However, its execution imposes some challenges.
We spend a lot of time doing the visual inspections, trying to find defects on the track.
In Metro DF, maintenance teams are only allowed to access the track during the maintenance window, which spans the period between 40 minutes past midnight and 4.5. This time frame is relatively brief, particularly for tasks that require meticulous observation of track details, given the slow pace of such activities. The second challenge is lighting. Since the work is performed at night, solely with the aid of flashlights, many defects go unnoticed in their early stages, thereby increasing the degree of deterioration until they are corrected.
One of the most recurrent defects in the rail track in Metro DF is the aluminum thermic welding. We have this shape of a candle, giving us the problem on the line.
The third challenge is the lack of an automated historical file for statistical analysis of nonconformities and trends. The existence of such a file would enable the identification of patterns and the development of preventive maintenance strategies, reducing costs and enhancing maintenance efficiency.
From the content presented in modules 2 and 5 of this course, and driving by previous studies conducted in the company, the idea of developing equipment to expedite and enhance the identification of defects in rails emerged. By using Arduino programming in conjunction with a control board, an accelerometer, and a GPS sensor, it was found to be possible to obtain graphs of vibrations caused by the wheel-rail contact. The main idea is that the accelerometer, being a sensory device capable of measuring acceleration on a specific axis, could capture the amplitude, frequency, and direction of vibrations, identifying shocks and impacts. Using the equipment along with artificial intelligence to read and analyze raw data, we will be able to identify patterns for each kind of track defect, even in its early stages, and monitor the evolution of a specific problem over time, allowing a proactivity planning. Furthermore, the acquired data will be organized in a single database, from which indicators such as defects per kilometer, quantity of defects corrected per month, monthly costs of rail maintenance, and annual cost of acquiring new rails will be generated. When analyzing possible locations for equipment installation, such as bogies, wheels, axles, and couplings, the decision was made to use it in the pilot's cabin. This choice considered risk analysis through the FMEA tool and provided better control for initial data collection, with the main focus on validating the solution. Additionally, it was decided to only perform readings on trains of the 2000 series in Metro DF until a sufficient level of device knowledge is achieved. The 2000 series trains record a higher volume of data, essential in this initial phase for the project, such as point-to-point speed and weight, as both variables can influence vibrations readings.
With the aim of testing the solution, we specifically choose defective welds as they should to be detected by the equipment. As the train passed over these faulty welds, we anticipated abnormal vibrations identifiable by the prototype sensor. For the tests, we defined a control section between 114 substations outside the tunnel and shopping station, thereby reducing the amount of data to be processed and validated. The equipment was installed on the pilot's cabin panel as determined after risk analysis. During the analysis, the equipment recorded abnormal behavior in the train's operation when passing over a defective weld. However, challenges remain to be overcome to ensure the reliability of the equipment, such as determining the ideal speed, appropriate weight, data transmission, and integration with GPS, as will be detailed throughout the presentation. We understand that this result, along with others to be presented here today, is encouraging, demonstrating that the project indeed has real potential for development and could be an excellent low-cost option to assist in maintenance.